Welcome back to Non-Convective Wind Shear. We're going to look at the physics of wind shear now, and there'll be no equations, so there is no need to fear. What we're going to do is look at reference frames. We're going to look at two different reference frames, one with respect to the airplane, the other one with respect to the surface of the Earth. Newton said that Newton's law of motion, or inertia, said that every body continues in its state of rest or constant speed in a straight line unless it's compelled to change because of forces that are acting on it. So Newton's law of motion, or law of inertia. So if we look at an airplane, here we're just looking at the airfoil. And the airfoil is moving through the air because of some sort of propulsion, which we don't show here. We're just showing the wing itself. It's moving through the air at, let's say, 135 knots. So the wind that it sees approaching the wing is 135 knots. So that's what's helping the aircraft fly is the airspeed, generating lift and other forces. And if that wing is an air mass that's moving, then the wing doesn't see that air moving past the wing. That's the wind, and actually the wing is moving with that air mass. So, you could say hypothetically, if the wind was 135 knots, or 135 knots, then the wing would be hovering right above the ground. And you probably experienced that. For those of you who fly, probably have done that in slow flight. Some days when the wind is really strong, let's say 40 or 50 knots, you could put the airplane in slow flight and you can hover over a point on the earth or even go backwards sometimes. So that's the concept we're talking about here. Let's use the numbers that we have in this slide. So moving through the air at 135 knots, wind is moving in the opposite direction. You got a headwind of 30 knots. That means that you're moving over the ground. Your ground speed is 105 knots. So if for some reason you were close to the ground and you hit something on the ground, whether it be a tower or a mountain, the damage that would result would be a result of your ground speed, 105 knots. Once again, if you use the analogy of a really strong wind and the wind was 135 knots, then your ground speed would be 0, and you could actually land with very little or 0 ground roll. You could just touch down. The airplane could touch down. What a concept. Anyway, so you're moving over the ground at 105 knots. That's your ground speed. And that's the energy that you have with respect to the Earth. Let's say instantaneously you had a change in wind. It went straight from a headwind to a tailwind. And in that regard, or that aspect, all of a sudden you will see wind coming from your tail at 30 knots. The airplane continues to move over the ground, however, at 105 knots initially. The airplane has inertia, and it's not going to accelerate or decelerate at that instantaneous shear. So it just moments ago was moving over the ground at 105 knots. You had this instantaneous shear of wind 30 knots from the tail. As a result, with that shear, with that change in wind, since the wing is still moving over the ground at 105 knots initially, you're going to see a loss of airspeed because the airplane can't respond to that shear fast enough. So as a result, the wind, the air going over the wing has been reduced by 30 knots, and now the airplane is moving through the air with respect to the air at 75 knots. Still moving over the ground at 105. That's your ground speed. That's with respect to the ground. That's the energy that the airplane has. But it hasn't responded to the air yet, the motion of the air. It's not moving with the air yet. So as a result, it sees 75 knots over the wing. And because of that, you saw a loss of airspeed, and also the airplane will lose lift and will start to descend. After a period of time, the airplane will, of course, descend, and as it descends, it accelerates and it gets back to its trimmed airspeed of 135 knots. When that happens, that 135 knots plus the 30 knots of tailwind gives you a new ground speed of 165 knots. But that takes some time. For airplanes that have little momentum, it doesn't take much force to accelerate to that airspeed. But airplanes that have a lot of momentum, we're talking larger airplanes, we're talking jets, 747s are massive, they have a lot of momentum. It takes a lot more force for them to accelerate. So smaller airplanes, a Cessna 150, of course it experiences shear, but it can accelerate faster through the shear because it has less momentum. Bigger airplanes takes a longer amount of time and more force to accelerate to the new airspeed to overcome the shear. So after a period of time, finally the airplane reaches its trimmed airspeed of 135 knots. It's got a tailwind of 30 knots. And now its new ground speed is 165 knots. But for that instant, as it goes through the shear, it'll lose some indicated airspeed. So that's the physics of shear. We're going to look at performance now. And when you encounter shear, how does the airplane respond? And we're going to look at performance, the aircraft performance, with regards to the shear profiles that we discussed in the previous video. And this is how the FAA asks questions on the instrument written test. They ask about these different shear profiles. So we'll go through the shear profiles and we'll talk about how the airplane responds. Once again, we said that how the airplane responds depends upon your flight path. Are you arriving to an airport, or are you coming in for a landing? Or are you departing an airport and climbing out? Also, it depends upon the shear profile. Does the wind increase or decrease with height?
Performance changes with low-level wind shear can either be classified as performance increasing or performance decreasing. Performance increasing shears means that you'll gain indicated airspeed and also notice either an increased rate of climb or a decreased rate of descent. Whereas a performance decreasing shear means that the aircraft will experience a loss of indicated airspeed and either an increased rate of descent or a decreased rate of climb. Performance increasing shears are caused either by an increasing headwind or decreasing tailwind shear. Increasing headwinds can be experienced as an aircraft ascends on approach and the winds get stronger closer to the ground, or as the aircraft climbs out and departs, where as it climbs, the wind speeds increase with altitude. Performance increasing shears can also be experienced with a tailwind, specifically a decreasing tailwind. So as an aircraft approaches the ground, the tailwind decreases, giving the aircraft better performance. Likewise, as an aircraft climbs and the tailwind decreases, the aircraft will also experience better performance. Performance decreasing shears can be experienced by either a decreasing headwind or an increasing tailwind. A decreasing headwind can be experienced either during approach or departure, and both of these are performance decreasing. On approach, as the aircraft gets closer to the ground, the wind decreases, which is a decreasing headwind. Likewise, as an aircraft climbs higher on departure, experiencing a decreasing headwind will result in a performance decrease. Performance decreasing shears can also be experienced with an increasing tailwind. For example, on approach, as an aircraft approaches the ground, gets closer to the ground during the landing, notice that on the left you can see the wind increases as a tailwind as the aircraft approaches the ground. So that increasing tailwind as it gets closer to the ground is a performance decreasing shear. Conversely, as an aircraft departs, if the tailwind increases with height, then that is also a performance decreasing shear. So that provides us a little bit of context for the physics behind shear, wind shear, and also how it affects aircraft performance. I hope you enjoyed this video and watch my other YouTube videos on non-convective low-level wind shear.